All right, looks like it's time to get started. We finished the first of two lectures on light last time, and we are currently still on schedule, the same schedule that's been up on the course web page where I post the lecture notes. And so today I'll give the second lecture on light. I hope you're all continuing to keep up with the homework that's on Mastering Astronomy and the quizzes posted every week at D2L. Are there any questions before I get started with the lecture?
Yeah, I got one question. I was on D2L and it said the next quiz was in May. So is there no quiz this week?
Well, so I'm sharing my screen right now. Why don't I log into D2L and we can look together. No, there should be quizzes before May. It's always possible that I made a mistake. So usually they become active on Tuesdays. So that's how I set them up. So let's see. The next quiz I have set up to begin February 9th on light, matter, and interaction. So that's the topic of last Wednesday and today, that lecture. And I believe it's chapter 4 in the text. Let me make sure that's the right chapter. I believe it's maybe chapter 5 is the chapter on light. Yeah, chapter 5 in the text is light. So you see that right here, quiz number 4. It becomes available on February 9th. And then it's will stop being available on February 12th. So you should see that. If you don't see that, let me know and I will check it out. But you may not see it until tomorrow.
Okay, thank you. That's what I was confused about.
Okay, any other questions?
I have a question. I got the textbook off Amazon, which maybe I did it wrong, but I can't find where I get the access code because my time is up tomorrow.
For your free registration? Yeah. So when you buy the there's a difference between just the textbook, right? You can just buy the textbook without any access to the website. You can also just separately buy access to the website through that website, right? When your registration ends, they give you the option to buy it. But you may have also, and I don't know, but you may have also bought a bundle, right? Sometimes you buy a bundle where they give you the textbook, and then on Amazon they do it a number of ways. Like sometimes you buy the textbook and it says with the code for Mastering Astronomy, and sometimes it actually comes with like a code when you buy the textbook.
Okay, thank you so much. Sorry.
Sure.
To answer your question, I bought the same thing, but the one on Amazon, I read the reviews. You buy the bundle, but it doesn't actually give you the code, so you actually have to buy it again.
So yeah, so some, of course, Amazon is sometimes a little bit of the Wild West. So I can't vouch for everything. I know there are, like I gave an ISBN in the syllabus that should be good, but people often find cheaper options. So I can't guarantee you, but you may have to follow up with them. It's not. So we're talking about light. We'll start with an overview. I mean, that's just a very important topic that will be used throughout this course. So let's start with a bit of an overview. Or review from last time. So light, the stuff that we think of as red through violet visible light is kind of remarkably actually has to do with magnets and the kind of static electricity you can feel with like a comb or petting your cat in the wintertime or something. It turns out to be a wave in electric and magnetic fields. We call it an electromagnetic wave. And all the different types of light are just different wavelengths, which in turn is the same thing, different frequencies. And it turns out at higher frequencies, mean smaller wavelengths. And that examples of that would be violet through ultraviolet, X-ray through gamma ray, higher and higher frequencies, smaller and smaller wavelengths. And on the other hand, long wavelengths correspond to low frequencies. Examples of that would be infrared through microwaves, through radio waves. Okay, and all of these waves go at the speed of light, 3 times 10 to the 8th meters per second, sometimes denoted C, and it's very, very fast. Okay, and also I talked about how if you take a light bulb and you dim it down so much that you can't really see it even with your own eyes, we have very sensitive detectors. You see that it comes in individual packets we call photons that each have an energy, and the higher the frequency, the higher the energy. And here's the electromagnetic spectrum. All of light ranges from radio waves, which are long wavelengths or low frequencies, up through gamma rays, which are very, very high frequencies or short wavelengths. And then also remember, because we just talked about that energy of each photon, it means that the higher energy photons are the ones to the right in this page. These are the things that can like damage cells and DNA and atoms. You know, you strike something with UV, X-ray, gamma ray, those individual photons have enough energy to hurt you. It's called ionizing radiation. Okay, and the visible part of the spectrum here, red through violet, is just a tiny, tiny sliver of the full electromagnetic spectrum. And so when we talk about looking at, say, stars and galaxies through telescopes, we're interested in that full electromagnetic spectrum, not just the visible spectrum. And when you see photographs in astronomy, it's not just going to be the visible spectrum. It'll be colorized so you can see it, but it'll also include visualizations using X-rays, using ultraviolet, using radio waves, and so on. Another review here, remember that light is a form of energy. We talked about all these different forms of energy, from kinetic energy, thermal energy, potential energy, chemical energy, like the calories you eat, light energy. Okay? Light is a form of energy. Those are a couple equations I just mentioned earlier, relating the wavelength. That's that Greek symbol lambda is wavelength times frequency is equal to the speed of the wave. And the energy of each photon is a constant times its frequency. And matter, this is the stuff that interacts with light, is made of atoms. And these atoms have a positively charged core called a nucleus that defines kind of where an element ends up in the periodic table. And then it's surrounded by an equal number of negatively charged electrons. And that's typically what interacts with light, those electrons. So one example of the sort of question that you should be able to answer really helps you understand electromagnetic waves, in other words, light, is to be able to reorder this list of light from, say, highest energy photons to lowest energy photons. Okay, so I'll do this one with you, right? So what does that mean? Highest energy photons means highest frequency. So these are ordering things from the right-hand side of the picture I showed you earlier of the electromagnetic spectrum to the left-hand side. So highest energy and highest frequencies are gamma rays, then X-rays, then ultraviolet, then visible, so violet through red, and then infrared, so that means below red, right? So ultraviolet is above violet, violet through red, and below red is infrared, microwave, radio wave. Okay? And I think it helps just to memorize that, it helps you just in your life. Whenever you hear these things, you now understand that they're all just, you understand their place in the electromagnetic spectrum. Here's a review question. So last time we talked about, what makes the sky blue, for example. We talked about that, and we did an example question about that. So as one review question that I'll ask, and it's the same concept, right? Why are sunsets red? Why are sunsets red? So let me bring up my poll, and I'll ask you this one. Okay. So the majority of people got the right answer. And this is the exact same answer as why the sky is blue. So remember, we talked about the sky is blue because molecules scatter blue light. The molecules in the air just scatter blue light more than red light. So what that means is if you look towards the sun, it looks less blue because the light that's white coming towards your eyes from the sun scatters away the blue light. So the sun looks a little redder, whereas the places other than the sun look bluer. And that's why the sunset is red, because during sunset, you're looking towards the sun and the light has course, is black body radiation. So this is still a bit of a review, but we're going to come back to this a lot because so infrared. So if we look at an elephant here through a thermal camera, you do see it glowing. It's glowing in infrared, right? Which is something that our eyes can't see, but it's still light. Whereas if you heat something up hotter, like this fire poker here, then it does begin to emit light in the visible part of the spectrum. It first starts to emit red, then you get hotter and hotter, and it starts to emit more yellow and looks more orange, and then yellow, and then it starts to emit even higher frequencies like green and blue. It doesn't typically look green and blue because remember, white is the color of the whole rainbow altogether. So once you're emitting green and blue, you're emitting red, yellow, green, blue, and then it looks white. And so when we talk about black body radiation, there's a couple things that are important. One is just the total amount of light that it emits. This will be important for stars, for example, and also planets. The total amount of light it emits has to do with its size. That's its area, right? The area that's emitting, right? So say a star or a human, the bigger you are, the more light you emit. And then it also depends on the temperature to the fourth power. Oops. Temperature to the fourth power. That is, the higher the temperature, the total amount of luminosity or power in terms of watts increases as your temperature increases very, very rapidly. For example, T to the fourth power means T times T times T times T. So if you increase your temperature by a factor of 2, if you double your temperature, you are emitting 2 times 2 times 2 times 2, that's 4 times 4, which is 16. So 16 times as much light if you just double your temperature. Okay. So that's called the Stefan-Boltzmann law. So bigger things and hotter things emit more total light. And then the other thing, the thing where I was describing the hotter something gets, the higher the frequencies of light it emits, or the shorter the wavelengths of light it emits, is called Wien's displacement law. Right? That just tells you, right, if you have a fire poker at room temperature, it's emitting infrared, it's glowing in the infrared. You get it hotter, it starts to glow red. You get it hotter still, it starts to glow yellow. Hotter still, it starts to glow blue even, although again, it looks white because you're combining red, yellow, green, blue all together. But what this curve shows is the peak wavelength is blue, for example. The most amount of light is at blue wavelengths, for example, at a certain temperature, okay? So the hotter you are, the higher the frequency of light you're emitting. Correspondingly, the shorter the wavelength. In other words, you get bluer and bluer, eventually ultraviolet, eventually X-rays, and so on. And we gave an example last time with the sun, right? The sun is an example. This is how we actually tell the temperature of the sun. Let's go the other way. Suppose we know that the sun's surface is 5,800 degrees Kelvin, right? So very hot, hotter than your oven, right? And we can use Wien's law to find out what is the peak type of light the sun emits. And we plug in and we find 500 nanometers. And all that is using this Wien's displacement law. It's a constant on the right-hand side. Temperature you have to plug in, and then you have to solve for the peak wavelength. And that peak wavelength, when you plug in 5,800 degrees for the temperature, is 5 times 10 to the minus 7 meters. That is 500 nanometers, 500 billionths of a meter. And that's green. That tells us that even though the sun doesn't look green because it's emitting, it looks white because it's emitting all the colors of the rainbow, the most amount of light is green. And it's not surprising then that our eyes are most sensitive to green light. So an example application of this that's really important in this course is how hot are stars, right? So based on what I've told you, you should be able to tell me, I'll work it out with you right now, right? Which star of these has the highest surface temperature? Well, blue corresponds to higher temperatures than yellow or red, or especially infrared. So infrared corresponds to something like at room temperature, like you and me. We are emitting infrared. But a red star is hotter than us. A yellow star is like our sun is hotter still. And a blue star is the hottest of these examples. Okay? So when we look at the color of stars, that tells us about their temperature. Now, a question, right? I've tried to emphasize this so far, but just to make it really, really clear, if all objects give off thermal radiation, why don't we glow in the dark? Well, we do, but in the infrared. It's not something that's visible to us, right? We only emit light that's invisible to our eyes, called infrared, right? But if you heat something up hot enough, it does start to glow in the visible part of the spectrum. First red, then yellow, then green, then blue. All right, any questions so far about just setting things up, right? The basics of how light is emitted, how much light, what color of light's emitted by things, what kind of light there is. Okay. Because one very, very important application of using light to learn something about the world when you look up at a star is the Doppler effect. Now, the Doppler effect, you're probably fairly familiar with from sound waves. So the Doppler effect is true of any kind of wave. We're talking about light waves here, but it's also true of sound. You have a car coming toward you, and then it passes you. The sound goes kind of like, right? First it's high pitched and then low pitched. You're probably maybe, whether or not you've recognized it, you're probably all familiar with that. That's due to the Doppler effect. That's because when sound waves are coming toward you, they get bunched up because the car is coming towards the sound waves. So as it's emitting them, they get bunched up. But then when the car goes past you, it's running away from the sound waves. So they get stretched out. And longer wavelengths sound lower frequency than shorter wavelengths. The same thing is true of light, okay? If a star is moving towards us, it looks a little bluer than if it's moving away from us. Then it looks a little redder, okay? When it's moving towards us, we say it's blue shifted, and it's moving away from us, we say it's red shifted. And not only does it tell us whether it's moving toward or away from us, but how fast it's moving, right? The more blue shifted it is, the faster it's moving towards us. The more red shifted it is, the faster it's moving away from us. And we can measure this really precisely because of those spectral lines we talked about, right? So, for example, in the laboratory where there's no motion, right, things are just fixed, we look at those really precise spectral lines when we put gas, like hydrogen gas, in a tube and light it up and heat it up and look through it with a prism. We see that it emits very specific wavelengths of light, like the specific wavelength of blue, the specific wavelength of green, the specific wavelength of red. And when we look at stars, we also see that because there's hydrogen in stars. So all we have to do is see if the star is moving towards us, then, well, first I'm going to talk about red shifted. So if the star is moving away from us, all these lines are shifted towards the red. So this red looks a little bit more of a deeper red. This dark green looks more of a yellower green. This blue starts to look towards green. They're all shifted towards longer wavelengths. And the faster stars moving from us, the more they're shifted towards redder wavelengths. And so you can actually measure that very, very precisely. So this is how we figure out that things are moving relative to us and how fast. We can do the same thing if something's moving towards us. Then instead of being red shifted, so this was red shifted, they're shifted towards us, towards the blue end of the spectrum. So here's blue, green, red again. If they're shifted to be bluer, so this red starts becoming orangish colored, this green starts becoming blue, this blue starts becoming violet. Okay, that tells us that not only is something moving towards us, but the degree of that shift tells us very precisely how fast a star or galaxy is moving towards us. Okay, so that's how we determine velocities, okay, in astronomy. And so before we had talked about how, so here's a summary of all of these different ways we learn about things from light that we talked about. We talked about composition, right? So we learned that if you take light through a prism, you see these very specific lines, and the placement of those lines correspond to hydrogen or helium or lithium or oxygen or nitrogen. They tell you exactly what things you're looking at. So you can tell what is out there by looking at the spectral lines. Okay, this is how we know what stars are made of. This is how we know what the composition of nebula are, the seeds that create new solar systems and stars when we look out in the sky. We'll talk a lot about that when we talk about the birth of stars. Okay, so we know what is out there. We know how fast things are moving through the Doppler effect, okay? And we know the temperature of things and the size of things from the thermal spectrum. That is, how much light something is emitting tells us about its size, its area, and its temperature. And its color also tells us about its temperature. Right? Bluer stars are hotter. Redder stars are cooler. Any questions about this stuff before I move on? So the next thing I want to talk about are telescopes. I'll just lighten the mood with an Onion article. Hubble kaleidoscope finds evidence of space looking all crazy. But of course, we are interested in looking out at space and observing all of these beautiful wonder. I mean, so there's so many wonderful pictures of things we'll see in this course, right? Taken through telescopes. And there's two main things we want in a telescope, okay? One is we want it to collect a lot of light, okay? We want our images to be bright because the further things are from us, the less bright they get. And for that, we want a big telescope. That's why we want one reason why we want big telescopes is we want to collect as much light as possible, okay? The other important thing is the resolution, right? We want to be able to magnify things, see things that are further away, right? So if the image is blurry, we can't magnify it. But if it's really crisp, then we can, and we can see things far away. Okay, we define the angular resolution, okay, as the the smallest angular separation. So remember we talked about things being separated by angles in the sky, right? Remember, like the moon in the sky extends across half a degree. The angular resolution is how close things can get in the sky angularly before they blend together into one object. So if two stars we see as distinct from each other, then we see, then we can resolve them. We have the angular resolution to resolve them. But if they blur together into just one blob, then we're not viewing them with enough angular resolution to visualize the difference, the distance between them. And this turns out to be about equal to the wavelength of the light you're using divided by the diameter of the telescope. In other words, so you want smaller angular resolution. So in other words, this is another reason why you want a big telescope. The bigger telescope you have, the better the resolution you have for a given wavelength of light. So we're going to go over these. So regarding light collecting area, right? You're wanting a bigger telescope. Here's a picture of the moon in the Andromeda galaxy, right? So I've emphasized to you just how amazing it is that if only your eyes were more sensitive, when you looked up at the night sky, you'd see this enormous Andromeda galaxy. This is the closest major galaxy to us. That is like 5-6 times bigger than the moon in the sky. But it's hard to see because you need a lot of, our eyes are too small to collect all that light. So what you need is either a really big telescope to look at it, or you can use the small camera, but you have to do a long exposure photograph to get enough light. Okay, so if Andromeda were brighter, this is what it would look like, or you just need a telescope with a really large diameter to collect enough light to see it clearly. Okay, the other thing is resolution, right? So you're all probably familiar with this, whether you realize it or not. Like say you're watching a car come towards you from far away, right? So there's a car coming towards you. When it's far away, at some point it looks like one point of light. Okay? That's because even though it has two headlights, at a certain point it's so far away, the angular distance between those lights is below your eye's angular resolution. But at a certain point, they get close enough to you that you can resolve those two separate headlights because now their angle is between them is larger than the angular resolution. The resolution of the human eye is about 1 arc minute, meaning a 60th of a degree. Okay. For someone with 20/20 vision, in other words, if you're looking at something in the sky whose angular separation is more than 1 arc minute, then you resolve two separate objects, like 2 points of light, 2 stars. But if they're closer together than 1/60th of a degree, 1 arc minute, then you'll just see them as one combined blob, one single star. To get a sense for what this means, right? If you have a resolution of 1 arc minute, what would it be if I digitized the photo with that resolution? So that's what I did here. I took a picture of the moon with the resolution of the human eye. That is, if your resolution of your eye is 1/60th of a degree, in other words, 1 arc minute, and the moon is half a degree, in other words, 30 arc minutes, then that means that if you're looking at the moon, you're really looking at the moon with like 30 pixels worth of resolution. So even though it looks pretty good when you're looking at it from far away, if I zoom in to something with 30 pixels of resolution, you can't get very, you can't see the details with the resolution of the human eye. So this is kind of what the resolution of the human eye would give. Zoom in towards the moon. By the way, that means that 1 pixel is equal to about 100 kilometers. So you can't resolve any features on the moon smaller than like big mountains, valleys. On the other hand, here's like the best optical telescopes, like the Hubble telescope. They have angular resolutions down to 1/1000th of a degree. So they're very, very good. So here I've done the same thing with the moon. So here's a moon with the resolution of the best Earth-based telescope, meaning this picture of the moon has about 200,000 pixels of resolution. 1 pixel is about 20 meters. So actually this is surprising. It means that still, even with the best telescopes, you can't resolve things down to smaller than about 20 meters. You can't even see like the moon lander that went up in the 60s. So here I've zoomed in. This gives you a sense for the best sort of features you can see on the moon with the best telescopes we have that can resolve features down to about a millionth of a degree. In other words, the difference between like my mouse here and here is about a millionth of a degree, and that's the size of each pixel. Here I just gave you kind of a list, to give you a sense for angular size of various objects. So if you want to know the angular size, this is why we went over those concepts of being able to relate sizes to distances to angular size, right? But the equation relating the angular size of something to its actual size and the distance from you is that the angular size is its size divided by its distance. Right? In other words, if I want to find the angular size of the moon or the sun, well, I find the size of the moon or the sun and then divide by the distance from us. And when I do that, I get that the sun or the moon's angular size is about half a degree. In other words, 30 arc minutes. And what I've done is I've put this in terms of Jupiters, just because I thought this was kind of interesting, because a Jupiter is about the resolution of the human eye, about one Jupiter. In other words, if you look at Jupiter in the sky, basically you just see one blob, one point. You can't really, with your own human eyes, you can't resolve, the stripes on Jupiter, or the great red spot, or the moon's separated from Jupiter. You just see one blob. So that's about the limit of the human eye. So the sun or the moon, in terms of Jupiters, they're about 50 Jupiters across. To put that in some context, if you take a penny and put it 10 meters from you, it'll be about 10 Jupiters across. Once you put a penny about 100 meters from you, that's about the limit of resolution of the human eye. It looks about like the same as looking at Jupiter in the sky. Which is also similar, by the way, look at like a red stoplight from a kilometer away, or an ink period on a sheet of paper from about 2 meters away. Those are also about the same as looking at Jupiter in the sky. Just to give you a sense for, right? Like when you look at Jupiter, how big is it in the sky? Okay, that's how big it is. Now Neptune, right? That's the furthest away of our 8 planets. That's very hard to see. It's about a tenth of Jupiter in the sky. Okay? The best, typical backyard telescope can resolve down to about 0.03 Jupiters. Okay? The Hubble's telescope, okay, or Pluto in the sky. So Hubble's telescope's resolution can just barely resolve Pluto. Okay, and that's about 1,000th of Jupiter, meaning the Hubble telescope can see about 1,000 pixels worth of resolution on Jupiter. That's also, by the way, like the largest star in the sky, Betelgeuse. So basically, the Hubble telescope can start to actually just barely almost resolve the largest star in the sky. And this, by the way, is why you don't see pictures like our own pictures of our sun, of stars, because they're so far away, even the biggest ones, we can't resolve with our telescope. The nearest star is even worse. Nearest star, we can't even get close to resolve with Hubble. And even worse, like, is the lunar rover on the moon. Like, if you want to look at the moon, the flag or the rover we put on the moon 50 years ago, that's 1 billionth of the size of Jupiter in the sky. It's so small we can't see it with any of our telescopes. We have to go there ourselves to see it. Any questions about getting a sense for like the size of things in the sky and the ability to resolve them with resolving power of telescopes? Here's an example, backyard telescopes can resolve some of Jupiter, right? They can't, you don't get those beautiful photos like we'll show you later in the course from probes that fly directly by Jupiter or of the Hubble telescope. This is the sort of thing a backyard telescope can do. Just barely resolve the moons. You see these moons, you can hardly tell that they're anything other than a point of light. One important thing is to understand that the smaller the wavelength of light you're using to look through a telescope, the better the resolution. Okay? The resolution of a telescope depends on both its size, so that's this D here. The bigger the D, the diameter of the telescope, the smaller the angular resolution, which is better. But also the wavelength here means that big wavelengths give us worse or larger angular resolution. That's because the waves are big. It's hard to resolve things with big waves. You need tiny waves to see tiny features. So here's just an example showing red light, yellow light, green light, blue light. You can begin to resolve. Whereas with red light, you couldn't resolve 2 points of light. They're overlapping and form one blob. With blue or violet light now, you can resolve. So the resolving power really does also, so radio telescopes are really great. We'll talk a lot about radio telescopes, but radios have big wavelengths. So they don't give us the ability to see really small features of things. They don't have good resolution. Alternatively, though, if you increase the diameter of the telescope, so even with radio waves, if you make a really big telescope, then the angular resolution does get better. So this is also showing, instead of changing the wavelength, just keeping, say, red light, if you make the diameter of the telescope larger here, that too can allow you to resolve, say, 2 separate stars. Okay, here's a question to get you thinking and understanding about what angular resolution means. So here, suppose you have an angular separation in the sky between 2 stars of 0.2 arc seconds, right? That tells you how far apart they are in the sky. Okay, and you photograph them with a telescope that has an angular resolution of 2 arc seconds. What would you see? So here, the angular resolution, the separation of the stars is less than the angular resolution. So the photo will only show 1 star, not 2, right? Here, your angular resolution is 10 times larger than the actual separation between the stars. In order to see 2 separate stars, you need your angular resolution to be smaller than the separation of the stars. So with that in mind, I will ask you this question. And so tell me, you have 2 stars that are 3 arc seconds separated, but you photograph them with a telescope that has an angular resolution of half an arc second. What will you see? Okay, here your angular resolution is less than the angular separation between the stars.
Huh.
I'll give you 10 more seconds.
Just one.
Okay, I'm stopping it. Okay, so this is like the opposite of the last question. So here, the separation between the 2 stars is larger, significantly larger than the angular resolution. So that means you can resolve in between the 2 stars. So here you will see 2 distinct stars in your photograph. So the majority of people got the correct answer. Although some people said 2 stars will appear to be touching, looking rather like a dumbbell. Well, no, I mean, so that would be the case in the in-between region. If maybe the angular resolution were about the same as the angular separation, that's where you can get into that region where they're kind of touching, but starting to resolve, okay? But here, the angular resolution is well smaller than their separation. Okay, any questions about that? So there's two main types of telescopes. There are reflecting telescopes. This was invented by Newton. They use mirrors to collect, magnify, and focus light. Right? The idea is to have a large collecting area. We use mirrors to collect that light and focus it down to a point that you can then use a lens then to focus into your eye. Okay, most big modern telescopes are reflector telescopes because you can make them much, much larger with mirrors, because mirrors are easier to make big. We can make big mirrors, but it's much harder to make huge, heavy discs of glass. Right? We can also send up into outer space mirror telescopes easier because they're lighter. So like the Hubble telescope is about, for example, 2 meters in diameter, has a pretty good small angular resolution of 0.05 arc seconds. But the world's largest reflectors have diameters up to even larger now than 10 meters, because we can make mirrors that are 10 meters in size. The other type that, for example, that Galileo used before Newton, use lenses. So it's like, the same technology from your glass, that you use in glasses. Use lenses to magnify and collect and focus light. The largest reflecting telescope, the Yerkes Observatory, is actually just over the border in Wisconsin. There's a picture next. Okay, well, in a second. There's a refracting telescope. So typically you have a big lens, and these, so you have a lens that collects light and focuses it onto then an eyepiece. Then focuses it for that last stretch into your eye. Yeah, here's the world's largest. So built over 100 years ago, operated by University of Chicago. And the world's largest is only 1 meter in diameter. So this is significantly smaller than the Hubble. So 1 meter in diameter, that's how big. And that's because a lens 1 meter in diameter is pretty huge. Here it is. So here's the size. Here's a person for scale. So you see it is enormous, but its light collecting diameter is only 1 meter. So nowadays we can do much better with reflecting telescopes. Here's the type of reflecting telescope designed by Newton. So light is coming in from the right. So the stars are on the right in this photograph. And the light comes in and it bounces off a mirror called the primary mirror. And then it is focused towards this little secondary mirror that then points the light back out into an eyepiece. So you typically, you're looking through the side of the telescope, whereas the light is coming in from the right. But there's lots of variations of this idea. So by the way, this can be very light, because this typically, this can be a cardboard tube here for, amateur astronomers. This could be just a big cardboard tube, and all that really matters is you have a big mirror on the end here, and then a little mirror here to focus light into a little eyepiece on the side. But you can have all sorts of similar ideas. So here's a different example, basically the same idea, but this is uses a secondary mirror to focus light out this end. So this way you can kind of actually look towards the stars. So the starlight's coming in here, bounces off this big mirror to a little reflector that focuses it so you can look into this end of the telescope. But it's the same basic idea. So there's lots of similar variations of the same idea. But at the end of the day, what you have to do is make a really good mirror here. That's the idea of a reflecting telescope. So examples, this was one of the big, most famous ones is in Hawaii, this pair of ground-based reflecting telescopes. It's called Keck Observatory. And here's kind of a nice little map of the sizes and shapes of a lot of the big main telescopes, including some that are currently being built here. So these biggest ones, this one, and this one, the kind of 3 largest ones are almost done, but not done yet. So here's the Observatory, the largest refracting telescope, very small on this scale, whereas Hubble is also pretty small on this scale. So here's Hubble. Because on the ground, we can build much larger telescopes. So here's the Keck telescope at Mauna Kea in Hawaii. So this is one of the largest telescopes currently in operation. enormous reflecting telescopes. But there's other large ones like the Very Large Telescope here. We like, we're planning to replace the Hubble with a bigger one called the James Webb Space Telescope. That should actually go up this year. Keeps getting delayed. These enormous ones keep getting delayed, but they should be ready soon. Now, there's this question: why do we have telescopes on the ground, but some telescopes in space? Right? It makes it way more expensive to put up a telescope in space. Well, the reason is because some types of light get absorbed by our atmosphere. So this shows which kinds of light can get through our atmosphere and which can't. So visible light can get through our atmosphere. So we can do ground-based telescopes with visible light. Same with radio waves. Radio waves, we can use ground-based telescopes. But infrared, but even to a larger extent, ultraviolet, X-ray, and gamma ray gets absorbed by our atmosphere. Some of it gets down, but a lot of it gets absorbed by our atmosphere. So for that reason, really advantageous to put some telescopes in space. Because otherwise, that kind of light we just don't see. Besides visible light, this is the other kind that really makes it to the Earth, and astronomical radio sources were first discovered in the 30s, so almost 100 years ago. And we can build really, really large radio telescopes because, first of all, it's pretty easy to make a big mirror for visible light, but it's even easier to make a big mirror for radio light because radio waves have such a large wavelength. If you want to reflect them with a mirror, you don't even need something shiny looking. You just need a bunch of metal, kind of the same way your microwave has that mesh of just metal on the front, and that keeps the microwaves from frying your face. That's a mirror for microwaves. Similarly, for radio waves, you just need kind of metal scaffolding. So you can build them very, very large. So the largest telescopes on Earth are called radio telescopes. Further, you can build a quote unquote larger telescope with, by just instead of building like an enormous single dish, you just have a bunch of smaller telescopes all across the world acting together. That's called interferometry. So we have huge arrays of many, many telescopes. One is called the Very Large Baseline Array that act together, kind of like they're acting like a single, much larger telescope. So examples of radio telescopes, Arecibo is very famous. Very sadly, it broke recently, like a couple of months ago. It was destroyed, and this is both famous and a very useful telescope, very large. But in addition, though, we have this concept of interferometry, where we have these huge arrays of radio telescopes. So this is a typical. This one's in New Mexico. So many, many radio telescopes arrayed out so that they can act as though that they're just one much larger telescope. It's a very, very large array. So these radio telescopes are really useful in astronomy. And so this is an example in this course where, in addition to visible light, you're going to see false colored images showing colors that are meant to represent radio waves. So here are two galaxies. They're called the antenna galaxies because so you see in visible light, stars and kind of in yellowish color are these two galaxies. But if you look at radio waves, these big antennas show up in blue. We call them antennas because they look kind of like antennas. So this blue light is from radio waves. Here's in Hubble captured this. So the thing in the center and these kind of everything that looks kind of yellowish is captured from the Hubble Space Telescope. But the Very Large Array that I just showed you a couple of seconds ago, in pink, is highlighting the radio emissions. So really interesting. This is a galaxy with weird things coming out both sides that we see that show up in radio. Here's another example, Fornax A, another galaxy. You can see from visible in the center, and then highlighted in orange. And so different colors are used. You can't. There's no general rule. Your orange is used to show the radio waves. Okay, so going back to atmospheric penetration, here's just another picture illustrating a whole lot of things about light. At the very top, it tells you, okay, radio waves penetrate the Earth's atmosphere, visible light penetrates the Earth's atmosphere, but what about ultraviolet, X-ray, gamma rays? These don't. And by the way, I like this picture because it also contains lots more information. It tells you the rough size, the wavelengths. So radio waves have huge, can be more than a kilometer, whereas visible light is like the size of little bacteria. Ultraviolet is the size of molecules. X-rays are the size of atoms. Gamma rays are the size of nuclei. It even shows you, the temperature you need to get different colors of light. Anyways, in order to see these wavelengths of light that don't make it through our atmosphere, notably microwave, infrared, ultraviolet, X-ray, gamma ray, we need to send up satellites. So NASA, for example, has this great observatories program trying to see all the wavelengths of light in the sky. And so telescopes that really advanced our understanding, what was the Compton Gamma Ray Observatory. So we sent that up, looks for gamma rays. Chandra X-ray Observatory looks for X-rays. Spitzer Space Telescope looks for infrared. Okay, and also Hubble Space Telescope, that looks mostly invisible, but we'll talk about why it's also important to get up above the atmosphere, even for visible light. And these have successors now, not just NASA. We aren't leading anymore. Now the European Space Agency is really big. But anyways, these have successors. Hubble is soon to be replaced by the James Webb Space Telescope. Compton was replaced by the Fermi Gamma Ray Telescope. And Integral from the European Space Agency, that's what ESA stands for. But anyways, at any given time, we always have these telescopes that can see all these different wavelengths of light. And you'll see pictures in this course that integrate sometimes all of these together to paint a more complete picture of what we're seeing in all the different waves of the electromagnetic spectrum. So we've got these covered: Spitzer for infrared, Hubble for visible, Chandra for X-ray. And you'll see, here is the Andromeda Galaxy, for example, and a bunch of different wavelengths of light. So here's visible. You look at it with the Hubble, this is what you see for this big galaxy in the sky. Okay, but you can use Chandra to get the X-rays, right? You can look at ultraviolet, you can look at infrared and radio waves, okay? So all these things tell a different story about, and that we'll talk about in this course, about what is in the Andromeda Galaxy. We can look at it visible, see certain features. We can look at it in radio waves, see other features, look at it in X-rays, learn other things about it. Same with other objects. Nebulae, okay? Here's the Crab Nebula. This is from that supernova that happened 1,000 years ago, right? It's the remnant of a exploded star, this kind of expanding cloud of gas and dust. We could look at it in radio waves, infrared, visible light, ultraviolet, X-ray. Interestingly, and as we'll talk about, right? Something interesting going on that's very, very hot, emitting X-rays near the center where the supernova happened. So we'll talk about that. Okay, and then you'll see composite images, right? Here is a famous pinwheel galaxy where we see both visible light from Hubble, but also X-ray from Chandra overlaid on top of it, different colors. Here's a cluster of stars. And we'll talk about in this course how we learn so much by, so this is showing 3 different sources of light. We see blue from X-rays, telling us about where the hot gas is emitting X-rays. We see infrared, showing up in red and orange here, telling us what's kind of at room temperature. And we see optical kind of showing up in yellow in this picture, okay? This is tremendously powerful, being able to look at objects, not just in visible light, but suddenly a whole new world opens up. It tells us a lot more when we can look at other wavelengths of light. Now, any questions so far?
I was like, how do we interpret like the radio waves and the X-rays and stuff? Like, because it's not a color, because that would be on the visible spectrum. So I guess I'm just wondering how.
Yeah, so I mean, so when these, when we the real pictures we get from these telescopes are black and white, because as you say, there's not a real color for. So say we're looking at X-rays. When you look at, like, if you go to a doctor's office and you see an X-ray of your bones, right? What you're seeing is a black and white image, because what it's showing, what's dark is showing what in an X-ray is showing what didn't absorb the X-rays, and what shows up brighter shows what did absorb the X-rays, right? And that's the same thing we're doing. It's black and white photographs. So in an X-ray picture, we see where are the X-rays will show up brighter in our black and white image, and where there aren't X-rays will show up darker in our black and white image. But then if we want to show a picture of where we already took a visible light picture, that has the colors of the rainbow in it, but we want to add to additionally show that black and white image of X-rays, we want to distinguish it somehow by allowing people to see where those X-rays are coming from. So then we typically do a false color, right? We'll like in these photographs here, right? We'll add a color. So here it's orange, right? And there's no general rule for what color that is. It's just something that will help people see what, in this case, it's radio waves, right? Because they colored it orange in this image, because you're probably not going to confuse that with the rest of the visible light spectrum. So it's tough, right? It's hard to do this. You just kind of, it's almost more, in terms of making pictures, it's almost more art than science. Of course, when we analyze these scientifically, we just keep them separated. We just have our black and white X-ray image and our black and white infrared image. But for seeing everything that's going on at once in astronomical photography, we do false color imaging. So we can see in this one photograph, we see invisible where the galaxy is here, and then in orange we see where all the radio waves are coming from, which is just a very interesting amount of information in this one photograph.
Okay, cool. Thank you.
Any other questions? So there's another reason why we might want to put a satellite up instead of a ground-based telescope. That's because stars twinkle. The only reason stars twinkle is because of our atmosphere. It's the same effect as when you see a mirage on a hot day. You're looking down the road and that hot air is causing, the things in the distance to kind of be wobbly. It's the same thing that happens when stars are twinkling. It's because the atmosphere, it's the same thing that causes turbulence if you've ever flown. Sometimes there's pockets of warmer air that's because it's warm air expands, it has lower pressure. Sometimes there's pockets of colder air and it cools down and bunches up. And as you're looking at a star, you're seeing pockets of warm and cold air and causing the light to get bent in different ways. And it causes stars to twinkle. So if you're an astronaut, the stars don't twinkle anymore. That's just an effect of being below the Earth's atmosphere. We call that atmospheric turbulence. Okay. And because of that, because the stars are twinkling and wobbling around, under the best conditions, the resolution of any telescope is about 0.4 arc seconds. Okay, in other words, any telescope more than about half a meter in size, you're not going to do any better with visible light, for example. Okay, because you're doing really well with your telescope, but then your stars are wobbling around. There's the same effect if you have a grill, right? The air shimmers above the grill. That's also an example of atmospheric turbulence. Okay. So one way of solving that problem is to send up telescopes into space, like the Hubble Space Telescope. That's why the Hubble, even though it's not super big, takes some of the best photographs because it doesn't have to deal with atmospheric turbulence. But in the last few decades, there's been kind of a revolution in ground-based astronomy that uses what's called adaptive optics. Okay, so here's a deformable mirror. This is a computer-controlled mirror that can actually make tiny deformations to try to compensate in real time for atmospheric turbulence. So, like, here's an example. We have these two observatories sending lasers out into the sky, and they know where they're pointing the lasers, and they can watch. Does the laser twinkle? If the laser twinkles, then they know exactly how to deform their mirrors in order to keep the laser straight. And in that way, they're able to do much, much better than they used to. Still not as good as like the Hubble, but it's getting much, much better than it was 30 or 40 years ago. Here's some examples, right? Uranus, it used to be with ground-based telescopes, this was the best we could do. Now we can actually photograph Uranus pretty well from ground-based telescopes. Center of the Milky Way, huge difference with using adaptive optics. And so now the major big telescopes that are built use adaptive optics, that is actual deformable mirrors and lasers to in real time slightly change the curvature of the mirror in order to compensate for any, for what's going on in the atmosphere. Any questions?
I have a question.
What?
So like the laser is kind of like a sensor, and it sensors the and then there's a computer that changes the mirror, like to make the line straight, I guess.
Yeah, like so the laser is acting as a reference, meaning you want something that you know should be straight. So if you see that the laser is suddenly wobbling or bending, well, it shouldn't be bending. You know that that's due to the atmosphere. So then, yeah, you use computers to deform the mirrors until the laser looks straight again.
Okay. Thank you.
Any other questions? Okay. All right, I'll let you go. I will see you on Wednesday.
Thank you, Professor.
Thank you, Professor. See you Wednesday.
Thank you, Professor.
Thank you. Thank you.
Well,